Welcome back to Jameel Cast, where we explore ideas and innovations shaping the future of our world. Join us as we uncover perspectives and insights at the intersection of purpose and progress, featuring voices from across Abdul Latif Jameel's international network of businesses. This is Alex, your AI host. Today, we're exploring a technology so precise it could unmask the universe's greatest secrets, yet so practical it could improve our daily commute. We're talking about quantum sensing. To help us unpack what this means and why it's poised to be so transformative, we're joined once again by our AI guest, Sophie.
Thanks, Alex. It's a pleasure to be here.
Sophie, the claims about this technology are enormous. We hear it could solve cosmic mysteries while also making our lives safer here on Earth. Where do we even begin?
It's true, the scope is vast. Perhaps the best place to start is with one of the biggest mysteries in physics: dark matter. It's the invisible substance thought to hold entire galaxies together, yet we've never been able to detect it. Quantum sensing is set to change that. Researchers plan to use microscopic sensors that vibrate when exposed to incredibly weak forces, allowing them to, for the first time, potentially see dark matter via its interaction with quantum light.
So, a technology powerful enough to find the building blocks of the universe. That's incredible. But does it have applications outside of a theoretical physics lab?
Absolutely. Its real-world impact is potentially just as profound. Think of more sensitive warnings for natural disasters like earthquakes and tsunamis, because we can detect subtle tectonic shifts, or highly detailed maps of underground tunnels and utilities for safer urban planning. It also promises ultra-precise geolocation for autonomous vehicles far beyond what GPS can offer, and highly refined medical imaging for doctors. It's a foundational technology that will enhance travel, medicine, safety, and industry.
So the potential applications range from the cosmic scale right down to the pipes beneath our feet. That's an amazing spectrum, which brings up the key question we need to tackle. What exactly is quantum sensing? How does this technology actually work at a fundamental level?
At its core, quantum sensing uses the unique and frankly strange properties of quantum physics to measure the world with incredible precision. Think of things we can't easily perceive, like tiny magnetic fields, subtle gravitational variations, or minute shifts in motion. Quantum technologies can turn delicate quantum systems, the very building blocks of matter, into measuring devices of extraordinary sensitivity. It's about listening to the world on a scale we've never been able to access before.
Okay, so it's about using these delicate quantum systems as detectors. But how do you get a meaningful measurement out of a single atom or a photon?
It's a three-step process. First, engineers prepare a controllable quantum system, maybe a handful of atoms, into a very specific, known quantum state. Then, they allow that system to simply interact with whatever they want to measure, a faint magnetic field, for instance. Finally, they analyze how that interaction changed the system's quantum state. Because these states are so incredibly sensitive to their environment, even the tiniest disturbance leaves a clear, measurable signature. That extreme sensitivity is the real game changer here.
So that sensitivity is the key difference. Are there specific quantum concepts that give it such a huge advantage over our traditional sensors?
Absolutely. Two concepts especially amplify this effect. One is quantum coherence, where a particle can maintain its fragile quantum state long enough to accumulate information about its environment. Another is quantum entanglement, where multiple particles become linked. A measurement on one instantly tells you about the others. In a sensor, this helps filter out background noise and boost the signal we actually want to read, enhancing precision far, far beyond what any classical device could ever achieve.
So those concepts, coherence and entanglement, are obviously incredibly powerful. It makes me wonder how much of this is still theoretical versus what's actually happening in the real world. How far along this quantum sensing pathway are we really?
That's a great question, because for a lot of people, the answer is surprising. We're already using first-generation quantum sensing. The atomic clocks that form the backbone of GPS systems are a perfect example. They exploit the incredibly stable and predictable quantum energy levels within atoms to provide the precise timing that GPS needs to function. Without this quantum effect, our navigation systems simply wouldn't work as well as they do.
Okay, so we're already using them, maybe without even realizing it. But what about the next generation stuff? The devices that sound like they're coming from a sci-fi movie.
Right, those are emerging from the lab now. We're talking about devices using things like ultra-cold atoms, superconducting circuits, or even tiny defects in diamonds. These are designed to pick up signals far weaker than anything we could previously detect. They're starting to unlock capabilities like navigation systems that work without satellites, ultra-sensitive medical imaging, or instruments that can map underground structures just by measuring tiny shifts in gravity.
That's an incredible range. It sounds less like one single new tool and more like a fundamental technology that could impact dozens of different industries.
Well, yes, exactly. The potential applications are vast, from healthcare and geology to space exploration and environmental management. Because the field is so broad and, let's be honest, complex, it can be hard to grasp the practicalities. I find it's often more instructive to look at its application in a few specific areas like disaster detection to really understand the potential.
That's a great point, Sophie. You mentioned disaster detection as a way to make all this tangible. Could you walk us through that?
Of course, think back to the tragic 2004 Indian Ocean tsunami. What if we'd had advanced warning? That's a key driver for this research. In the UK, for instance, there are two fascinating approaches. One project, in partnership with New Zealand, aims to use our existing seabed fibre optic cables for quantum interferometry, turning them into a network that can spot early signs of earthquakes. Another is developing cold atom sensors to detect the minuscule gravitational shifts caused by shifting landmass before a quake.
Measuring gravity shifts from the ground, that's incredible. I imagine that has applications beyond just earthquakes?
Absolutely. Volcanic eruptions are a prime example. Traditional seismic sensors often miss the signs of sudden, devastating events like we saw in Guatemala and New Zealand. To tackle this, a French company, Exail, is now testing absolute quantum gravimeters on Tenerife's Mount Teide. These devices work by cooling a cloud of atoms and precisely measuring its acceleration during freefall. This can reveal telltale gravity changes caused by magma moving deep underground, offering a potential warning system where none existed before.
So this technology could help us foresee these imminent disasters, but can this same principle apply to slower moving threats like climate change?
Yes, that's the next frontier. The EU is funding a project to put highly sensitive quantum accelerometers into orbit. The goal is to build an unprecedented, high-resolution gravitational map of the Earth. From space, these sensors will be able to track subtle changes like glacier melt and sea level rise with stunning accuracy. That quality of data could completely transform our climate models and help guide our mitigation strategies.
Sophie, building on what you said about mapping the Earth from space, can this technology also bring clarity to the world we can't see, the one right beneath our feet?
Exactly, Alex. It brings to mind Arthur C. Clarke's quote where he said that, "Based on your own perspective, any sufficiently advanced technology is indistinguishable from magic. Quantum sensing effectively gives us the ability to see underground. Using quantum gravimeters, we can create incredibly detailed subterranean maps that go far beyond traditional ground-penetrating radar. This allows us to detect underground, voids and structures without the cost or the risk of invasive drilling. It's about making the invisible visible with a new level of precision we've just never had before."
Making the invisible visible, that sounds powerful. I imagine that has huge implications for the safety of our existing infrastructure.
It absolutely does. Think about aging utility and transport tunnels. They can develop stresses or cracks that are difficult to assess, sometimes leading to disaster. We saw this with a tunnel collapse in India in 2023, which was blamed on unforeseen geology. With quantum gravimeters, surveyors could monitor this infrastructure, detect weak points, or even assess subsurface suitability for new construction. It's a proactive way to prevent catastrophic failures and ensure public safety by understanding the ground we build on.
So from safety to resources, can this underground vision also help us locate valuable materials more efficiently?
Yes, and it's a game changer for exploration. Different quantum sensors can pinpoint valuable resources. For instance, diamond-based magnetometers can detect minerals like lithium and cobalt, essential for the green energy transition. A great example is Glencore's nickel mine in Quebec. Their quantum gravimeters created a 3D ore map that was 9 times more precise than traditional methods. This leads to more efficient drilling, lower costs, and a significantly smaller environmental footprint for resource discovery.
That Glencore example is fascinating, Sophie. It sounds like major players are already seeing a return. Is that success translating into wider investment momentum behind quantum tech?
It absolutely is. What's encouraging is the health and diversity of the market. You have established giants betting big, from tech stalwarts like Sandbox AQ, which is out of Google's parent company, Alphabet, to defense contractors like Lockheed Martin and Honeywell. These aren't just exploratory investments. They represent serious commitments from major industrial players who see a clear commercial and strategic path forward for quantum sensing. It signals a real maturation of the industry.
So it's not just startups in a garage then. This is established capital moving in.
Exactly. But the startup scene is also incredibly vibrant. Specialist disruptors are emerging all over the world. You have companies like AO Sense in the US building atom interferometers for navigation, Atomionics in Singapore creating portable gravimeters for resource discovery, and QCTRL in Australia developing software to stabilize the sensors themselves. It's this combination of established players and agile startups that's creating such a healthy, competitive ecosystem.
And what about the public sector? With all this talk of infrastructure and defense, are governments getting involved?
They are, and at a massive scale. The US Department of Energy has outlined $2.5 billion in funding this decade. The UK's National Quantum Technologies Programme is bankrolling research for infrastructure monitoring. And China has a huge network of national labs focused on quantum sensing. This public investment is critical because, frankly, the technology still faces hurdles. The price tag is steep, and the systems can be sensitive to environmental interference like vibrations or temperature changes.
So what's the path to overcoming those challenges?
It's really about tackling 3 things: cost, size, and standardization. Progress is being made on making the kits more compact. Some magnetometers are now toolbox-sized. We're also seeing AI being developed to filter out environmental noise and improve sensor stability. As we solve these engineering challenges and create common regulatory rulebooks, we'll move quantum sensing from the specialized lab to mainstream adoption. The pieces are definitely falling into place.
If there's one thing to take away, it's that quantum sensing is giving us a new superpower. The ability to see the unseen, whether it's detecting faint gravitational shifts before an earthquake, finding critical minerals without invasive drilling, or even peering into cosmic mysteries. This technology is rapidly moving from the lab to our world. It promises to make us safer, smarter, and more efficient in almost every industry.
It truly is about making the invisible visible.
Sophie, a huge thank you for sharing your incredible insights with us today. And to everyone listening, thanks for tuning in. You've been listening to Jameel Cast, the official podcast of Abdul Latif Jameel. For more insights and conversations shaping our future, follow us wherever you get your podcasts or visit alj.com to read our Perspectives articles. Thank you for joining us, and until next time, stay curious.